Log on, tune in, find out. Another good idea from Cambridge.
Which I have a suspicion is vaguely related to the last one, from Patan.
Yes, indeed. Thank you. Together with Dariusz, we offer you today a package. So, fortunately, I can spare some time because what I want to say is about the extensions of the presented ideas towards the sensor networks, which have the ability to move, reconfigure, let's say, in time. Those are usually called the mobile sensors. According to the Bell's law, not so famous as the Moore's laws about the doubling the computational power every 18 months, the Bell's law says that every decade a new class of computing systems is developed. So the sensor networks emerged in the middle of last decade. They can be considered as a subclass of the computer networks, ad hoc computer networks. However, they changed the way of thinking about the distributed measurements when you have to monitor some phenomena, some physical phenomena, which have the property of spatial dynamics, of spatial evolution. Such kind of systems revolutionize the paradigm of distributed sensing. According to increasing power of computing systems and developments in networking and producing low cost, maybe not so powerful, but very low cost electronic devices which are miniaturized, we are able to build extremely complex measurement systems which can provide a very rich data which will be used further in order to produce accurate forecast of the evolution of the system, or accurate control for accurate, let's say, predictions for controlling this system. Typical operations include sensing, of course, processing. So every sensor node have the small computational power, so it's able to process the data at least to some extent. Of course, one of the main operations is exchange the data with other sensor nodes. So we have to include the radio subsystem in every sensor node. Surprisingly, receiving the data and sending the data costs almost the same amount of the energy. So from this point of view, usually sensor nodes are sleeping almost all the time and are just doing a very scarce measurements. So when we have a lot of a swarm of numerous sensors, from the individual point of view, probably the most important thing we have to remember is to spare the energy, because every sensor usually is supplied by the limited battery. Okay, so that will show you a few applications which are stemming from real-world problems. So I'm not trying to show you the same pictures, because those are very examples, but I want to just express that those are real-world systems. It's not a science fiction. Probably the military applications are very spectacular, but what we are really interested in is air pollution or air quality monitoring. So this is a real network working in London Air Quality Network. consisting of few hundreds of monitoring stations. Some of those monitoring stations are stationary. Some of those monitoring stations are mobile in the sense that they are conveyed by cars. Of course, the main reason of existence of such observational system is to control the level of the air pollution, because in the big cities it's a really big problem nowadays. So in London, in Berlin, in let's say rich cities, they can afford for such observational system, because you can imagine that such monitoring stations are quite complex and expensive devices, and the real challenge is to how to utilize this efficiently in order to produce good predictions of the development of the smog, for example. As you observe every day the weather forecasts, so you can imagine it's a really difficult and challenging problem. Another representative example of application of sensor networks is intelligent building monitoring, in order to spare some energy to control the evolution of the temperature, for example, and many other things along the building. Extension of this is mobile warehouses, so there is a great potential of the sensor networks within this area. If the sensor nodes are conveyed, for example, by autonomous robotic vehicles, often called unmanned ground vehicles or unmanned aerial vehicles, we can call that the sensors have some level of the mobility and are usually called mobile sensors. I was attending in December control decision conference in Atlanta, and the sensor networks have some strange extensions, because there was military applications where the soldier was had the sensors, chemical sensors attached to his uniform, and he was called just mobile sensor. So it not necessarily has to be robots or robotic autonomous devices. We can go further, and using your mobile phone, which has a lot of sensors included, and you are already within the network. So all of can be considered as an extension of the mobile sensors. So it's a pretty funny story, but okay. What can you obtain with such mobility? Of course, we believe that the sensors having ability to move to some areas along the time interval can follow the temporal development of the physical phenomena. So we can go to the areas where something interesting is going on. So probably it's quite intuitive that the sensor should move to the areas where at given time instant the measurements will be most informative and provide a good data which can be used further to identification of the system, to forecasting the phenomena, and so on. Yeah, it's for sure the mobility requires or introduces great complexity to the problem. So there is a lot of questions which immediately appear. However, we can expect at least that using mobile sensors we can decrease this complexity by using, for example, less sensors than in the stationary case. For example, probably the same effects, the same informative data can be obtained using just a few mobile sensors instead of 100 or few hundreds of stationary sensors. So that's why we go for this challenge and looking for more systematic approaches related to such moving sensor strategies. A very challenging scenario is the scenario of the chemical attack within the urban area. So we start with some activation of some pollution source which develops within time. We try to model somehow, usually for modeling the development of the plume, some partial differential equations are required. We deploy the swarm of mobile sensors which have the purpose of monitoring, of tracking the pollution boundary. So when the plume develops within the time, we try to move, so propose the trajectory of movement for sensors in order to properly tracking the contamination area. To give you a taste how to test this in the how to test such scenarios in the laboratory, let me introduce a project of our joint co-worker, Professor Yang Chen from Logan University, Utah. This is the student project. We have a glass cage. There are walls inside, so we have some kind of labyrinth of rooms. There is a fog machine. Probably I have the better picture here. There is a fog machine attached to the cage glass, and we can introduce the fog into the labyrinth of rooms. And what we have here is the swarm of 10 mobile robots. Very simple construction. However, they have infrared sensors in order to avoid the collisions with the walls, and optical sensors in order to track the boundary of the cloud. Surprisingly, such simple test bed, because of the micro scale of this test bed, it's even more difficult than the real world case, because we have to model the development of the plume using nonlinear partial differential equations similar to the Navier-Stokes fluid dynamics equation. So it's not easy to approximate in such small scale the phenomena. So what makes the solution really hard is, for sure, complex mathematical models which have to be applied. Usually, the process is described using the partial differential equations, and I have to express that it's not upon our choice, because we are not really looking for complex. Being an engineer, I'm always looking for simple model which can approximate with good accuracy the real phenomena. But believe me, in many industrial applications, only the partial differential equations give you this level of accuracy which can be used in controlling the process. So that's why we have to go for such complex, sophisticated mathematical models. But we obtain potentially ability to approximate the real phenomena with very good accuracy. So I'm going back to the pollution source identification problem, which will be the example we are interested in. The problem, of course, consists in designing the trajectories of sensor movements in order to provide the most informative data for the purpose, for example, of detection, quick detection, reliable detection of the presence of such pollution source or sources. And of course, after detecting the source, we have to localize it accurately, and so on. Quickly, we can go for even more challenging problem. So if the source is also moving and this trajectory of the source is unknown, the question is how to reconstruct such trajectory. So it's probably easy to see that the second problem is far more extremely difficult than the first. Okay, Dariusz already has presented the general description of the class of considered systems using partial differential sets of partial differential equations supplemented with some suitable initial and boundary conditions. The difference, the slightly different form of the presented model is that there is directly written term which is responsible in this case, which is responsible for the modeling of the pollution source. So in the literature, different models are considered. However, due to some numerical reasons and due to the flexibility of the modeling, here we have the model, which is a continuous approximation of the pointwise pollution source, which is most common used in modeling in the literature. So in such continuous approximation of the pointwise source, we have separate terms responsible for the intensity dependent on the set of parameters rho, and spatial distribution of the source dependent on the set of parameters b. The psi here is the trajectory, unknown trajectory of the source, which also has to be estimated, reconstructed. So in order to provide a proper finite dimensional form of the problem, we first have to parameterize the source trajectories. So we assume some functional form that there exists some function which can approximate enough with enough accuracy the unknown trajectory. This usually depends on the finite vector of the parameters responsible for flexible approximation of the unknown trajectory. So typical choices are just using some typical interpolation methods, for example, B-splines and linear splines or so on. Finally, we have to estimate a set of parameters related to the intensity of the source, spatial distribution of the source, and the trajectory of the source. So there is a lot of things we have to discover from the observations, which in case of the mobile sensor nodes takes the following form. For the simplicity, we assume that the state for example, the concentration can be measured directly. Epsilon here is the measurement noise, which is assumed to be Gaussian stochastic process uncorrelated in time. A typical approach is to use the least squares criterion in order to estimate the vector of the parameters theta, vector of the system parameters. Very roughly, we can start with formulation of our problem in terms of how to determine the trajectories for the sensor nodes as to maximize the estimation accuracy. A reasonable approach within the group, within the mainstream of the methods originating from experimental design theory, is to use as such measure the Fisher information matrix. It has the same, almost the same form from the notational point of view. There is no crucial difference than here compared to the Fisher information matrix presented by Dariusz in the previous talk. However, here we have, instead of sensor position, we have the whole trajectory of the sensor node. Oh, as usual, this is familiar for almost all of you, that we have different strategies of compressing, so achieving the proper accuracy. I will skip this in order to spare some time. When we're talking about the robotic vehicles equipped with sensors, it's clear that we have to impose some additional constraints because there is no robots which have enough power to go with any velocity in any direction. So there are natural constraints which have to be imposed to our problem. So we have to model the sensor, the dynamics of sensor movements. So here we have the vector of temporal sensor positions. Introducing such a vector, we can write down an ordinary system of ordinary differential equations describing dependence of the position of the positions of the sensors from some control. Usually, in the simplest case, we can consider this as, for example, velocities of the robots. Such constraints provides, of course, some level of regularization for the sensor trajectories, because usually, because of the numerics, we have to assume that the right-hand side is a function which is differentiable with respect to time, and this introduced some level of regularization for trajectories. So from this point of view, they won't be not only be measurable, but, for example, continuous. More formally, we can now describe the optimal sensor guidance problem as looking for the pair of controls for the robots and initial positions of the robots. So we can also, to increase the level of the optimality, optimize not only controls but also the initial positions. It is possible to introduce this easily into the problem in order to minimize some scalar measure operating on the Fisher information matrix. Trying to solve such problem directly, you can imagine it's quite a difficult task. Fortunately, there exists a simple reformulation of the problem. So introducing a quantity pi, which is nothing else as a Fisher information matrix with the defined observation horizon, we can reformulate the problem in terms of the equivalent linear Mayer optimal control problem. It is not easier to solve. However, such problem is throughoutly studied in the literature. So we can reach for ready-to-use numerical solvers, for example. So this equivalent Mayer problem just gives us the opportunity to not develop our own software, but reach for very efficient numerical solvers, and of course the mathematical foundations and properties of this problem can be found in the literature. The main impediments when trying to design the trajectories are that in order to design the paths for sensors, we have to know some nominal values. So in a sense, the designs are local. Probably the engineers are more interested in the online adaptive approach, not offline routine. And of course, the mentioned yesterday problems related to the inverse problem, the ill-posedness of the nonlinear least square approach. A potential solution to provide to overcome those difficulties is to make a combination of well-known techniques known from optimal design theory. For example, naturally we can split the observation interval into sub-intervals and provide similar procedure to sequential well-known sequential design. So within each interval we will repeat the processes of estimation of the parameters, and based on those parameters we can design a new trajectories within the next time sub-interval. Another problem related directly to the air pollution is to how reliably detect the source. So when it appears within our system, and how to then localize it with a good accuracy. So first, to focus your attention, not all of the parameters of the system can be used in order to, for example, provide a good detection, proper, accurate detection of the source. So we have to split the vector of system parameters into two parts. The first part is will be composed from the parameters which are useful for building a proper diagnosis, and rest of the parameters which still has to be estimated, but are not significant for our purpose of detection of the source. In such a way, we can formulate the source detection problem in a typical way of testing the parametric hypothesis of the equality of this part to some known nominal values which can give us the information if the system is in the nominal state or something happened, for example, some contamination is present within our area. Going further, it's possible to construct the simple log likelihood ratio test. It is very often used by engineers because there are, practical, let's say empirical evidences that even if such a test is not optimal, and it is proved from the point of view of mathematical justification, it's still often very well work in practice. So now, even for the problems when we know directly that such likelihood test is not optimal, we can still utilize this and obtain a suboptimal but accurate results. We have the also the very nice theorem by Goodwin and Payne that log likelihood ratio converges weakly to some variable from the chi-square distribution with p degrees of freedom. This gives us a very simple threshold test. So in order to detect the source, it is enough to compare the log likelihood test with some significance level taken from the chi-square distribution. The question is how to maximize the reliability of detection in terms of the application is how to minimize the probability of missed detection. So where the source is present and we don't want to miss this fact. The very natural answer, owing to the assumption that the sensor nodes provide the independent measurements, it's clear that the more sensor nodes we use, the more reliable data we obtain. But unfortunately, in many practical applications, the number of sensors is limited, so we have to look for some alternative solution. It can be shown also, the proper results are given by the Goodwin and Payne, that instead of increasing the number of sensor nodes, we can construct a better experiment. Construct in the sense, look for proper trajectories of the sensor movements in order to increase the amount of the information in the data. So it has been shown that we have to focus on the Schur complement of the Fisher information matrix, Schur complement related to those parameters which are required for the proper detection. And we can use this, you can use this criterion, well-known DS optimality criterion, in order to increase the reliability of the diagnosis. And what we've got here is nothing else as the sequential design. So we split the whole observational interval into many sub-intervals. And for each sub-interval, we alternate the analysis phase when we try to, based on the current estimate of the parameters, we try to predict the evolution of the system. Then try to design the trajectories for the next sub-interval. Then we go for the experiment phase, so we collect the data. And finally, based on the data, we try to use the log likelihood ratio. We want to answer the question if the source is present within our monitored area or not. And then we go to the step first and repeat the same procedure for each consecutive time sub-interval. So from the point of view of experimental design, is nothing else like a sequential design. The localization block, so once the source, pollutant source is detected, we have to localize it. So we focus on the different parameters. So the localization block seems almost the same. It's a sequential procedure. However, the difference is that during the localization phase, we focus our attention on different parameters of the system. So in these terms, it's different. Okay, so I'll go quickly into some numerical examples. Consider identification of the stationary source. So we model the transport chemistry process of the pollutant using advective diffusion equation, supplemented with some boundary and initial conditions. Here we use the very simple model Gaussian of modeling the active source. What we want to find, because the source is stationary in this case, instead of trajectory, we want to find just a localization where the coordinates of the source location and, of course, the intensity of this source. The parameter which is not interesting from the point of view of source detection is the tensor of turbulent diffusivity. So we want to focus on those three parameters describing the source. Of course, this kappa parameter also has to be estimated, but we are not focusing our main attention on this. So in our simulation setting, the purpose is to design the trajectories in this, because this is stationary source, so there is no adaptivity at the moment. We want just in the offline manner propose the trajectories for different number of sensor nodes, providing the best accuracy of the three parameters describing the source. For the sake of the clarity, very simple sensor dynamics has been used. We control the velocities, so the u is the vector of velocities in two directions, two spatial directions. Control constraints, the velocities cannot exceed some level, some maximum speed. So probably I will present quickly the results. Here we have the evolution of the system. So we have a circle of radius 1 kilometer, and from the beginning we have the active source of pollutant which starts emitting the substance into our area. The arrows denotes the wind velocity. So the velocity of the wind is changing, and according to this transport phenomena and some other factors like diffusion, turbulent diffusion, we have the pretty complex process of spreading the pollutant into the area. So the parameters of the source, so its proper location and intensity is unknown. We have to find how it works. So probably I go for animation. So the sensors approach the area from the left boundary, and we can see that after a few hundred seconds, the source is localized in terms that the sensors tend to find the location of the source. Because of the velocity constraints, again, because of the velocity constraints, the last sensor is not able to reach the area where the source is present. So that's why this trajectory is like this. It can be explained in terms that these sensors try to provide the information not about the coordinates of the source, but rather on the intensity and unknown turbulent diffusivity coefficient. We can see the same procedure for 6 sensors. Trajectories are very similar, owing to the assumption of the independent measurements. Probably those 2 sensors in the middle just So you can have the impression that we can use more and more sensors, and the trajectories will be similar, and just some new sensors will independently follow some trajectories which will be more informative in our problem. However, I have also the experiments which a number of 20 sensors, and there appear the problem that they have to exchange, the information, so the trajectories differs from here within the comparison within the 4 and 6 sensors. It seems that the differences are very insignificant, but the more sensor we use, the area is, so the problem becomes more, sorry, just okay. So I go to next. So the last example is I will present very briefly. It's more challenging, and here we have the mobile source. The equations look similar. This time the source starts emitting the pollutant not at the 0 time, but at the moment of 80 seconds. The source is moving along the parabolic trajectory. So the process, as you can see, the process is even more complex than in the previous case. Now we are using only 4 mobile sensors. Okay, here I've got the results. So at the beginning, the sensor follow some arbitrary trajectories, so just go in the direction of the center, and when the source appears, some of the sensors which are able to follow the source do it that way, but the last sensor is not able to reach on time the interesting area where the pollutant is emitted. So how to explain the behavior of this last one? It is difficult, but what is used here was the linear approximation. So the parabolic trajectory was assumed to be approximated with linear splines. So doing the design in the for the next consecutive time subinterval, we do linear interpolation. So you can say that this sensor, the last 4 sensor, just looking for the prediction, not for the real, what is going on in our system, but this trajectory design is based on the prediction, and the linear predictions force it to look in the area where there is nothing interesting. Here is the real trajectory of the source and reconstructed based on the data gathered within this experiment. So assuming that there is a lot of approximation, linearizations of the trajectory and so on, a lot of simplification within this example, I can say that this result, this reconstruction is pretty nice. I would say I'm quite delighted with such a good result. And quickly, standard deviations of the parameters estimated during the consecutive sub-intervals of time are decreasing in a way. So we improve the quality of the estimates along our time axis. Okay, so probably I will finish at this moment, so sorry for extending a little bit my speech.
May have one comment and one question. Beautiful presentation, but you're not necessarily should name this reactors robots. This is robots are very expensive and people don't like them. And if you use moving sensors on car or flying, let's say, airplane, then this is exactly the same. In fact, this robotics terminology is not necessary. But my question is about detecting sources of pollution. The time that you detect depends on initial sensors positions. Have you tried only starting from given points or just moving at random like Brownian motion?
Yeah, it's because the question is why I choose the initial time. There is no arbitrary information about what is going on in the system, so the arbitrary choice was to choose those corners, and but those initial positions can be optimized as well. It was done only for the purpose of the simplicity of simulation. That's all. But you have right. To increase the level of the accuracy, we should also try some other scenarios and just compare. And some arbitrary choice is typical engineering choice. There is no more than just intuition behind it. That's all.
Another quick question?
How sensitive is the solution to perturbation? So if I take a small perturbation of one of these trajectories, how much does that affect the solution?
Yes, from some, we have some empirical experience because we have done a lot of different scenarios. So it depends on the amount of the sensor nodes, because, for example, if you use 10 sensor nodes, the one which is not gathering proper data has very insignificant influence on the quality of the reconstruction of the source trajectory. But in a case when you use only 4 sensors and the one sensor is not gathering the properly, does not follow a real trajectory which provides a good data, the influence is pretty high, because the perturbances have many sources. It's about the numerical solution of the partial differential equations, the simulated noise, and of course even the controls are not accurate, because the real vehicles also follow some perturbations during the realization of the trajectory. So when the number of sensors is low, it may be a real challenge to avoid such kind of influence. But
we better stop there if you don't mind, just to be fair to the next speaker. Thank you very much indeed.